Hello everyone, we are honored to demonstrate ChainDash, an ad hoc blockchain data analytics system. This is a joint work with East China Normal University and AntChain. Web 3.0 is dedicated to building the Internet of Value based on blockchain technology, which advances the digitization of assets and related applications. The on-chain transactional data produced by user interactions with these applications is transparent and can be used for KYT, thus holding immense analytical value. It is worth noting that the KYT service is a crucial tool to detect abnormal behaviors for anti-money laundering and counter-terrorism financing. It requires ad hoc graph analytics to identify security incidents, which may involve a large number of highly correlated abnormal transactions within a specific period of time. Currently, it is practical to synchronize on-chain data to off-chain stores for analytics. Still, two requirements need to be fulfilled before enabling efficient ad hoc graph analytics over arbitrary time windows. The first is high data synchronization efficiency, which guarantees the freshness of real-time data. The second is optimal graph snapshot retrieval performance, which accelerates the ad hoc graph query processing. However, existing blockchain data analytics systems typically synchronize data in a sequential and blocked manner. Transaction receipts are pulled block by block and replayed one after another. Therefore, these systems fail to provide real-time data freshness. In addition, prior works on multi-version graph stores rarely address the retrieval of graph snapshots that are larger than memory. Retrieving out-of-core graphs from unoptimized underlying storage causes great overhead, precluding their use in ad hoc graph analytics of historical windows. To summarize, the inefficient data synchronization and limited graph snapshot retrieval capability hinder the efficiency of ad hoc graph analytics over both live and past time windows. To address the above limitations, we design and implement ChainDash. It functions as a middleware system comprising two key building blocks. The first is a highly parallelized data synchronization component, and the second is a retrieval-optimized temporal graph store. ChainDash implements a multi-threaded parallel pooling mechanism to optimize data pooling and furnish ample data for the state replaying phase. During the state replaying phase, ChainDash designs a DAG-based parallel replaying method. By analyzing read-write dependencies and determining the serialization order of conflicting receipts, ChainDash constructs a conflict graph to achieve transaction-level parallel state replaying. Moreover, to guarantee robust replaying parallelism in high-contention scenarios, ChainDash implements a finer-grade item-level parallel replaying. It replays items instead of transaction receipts by relaxing the transaction-level ACID requirements. Meanwhile, we set synchronization barriers to ensure the block-level data consistency. For the evaluation, we select the transfer events from USDT smart contract on Ethereum as data to be synchronized. We measure cumulative synchronization time of ChainDash, the graph, and Ethereum ETL. The results show that ChainDash achieves superior efficiency. It saves up to 83% and 49% process time compared to the other two solutions respectively. The graph store aims to support efficient graph snapshot retrieval. It comprises two techniques. The first is an append-only storage layout, and the second is an epoch-based index structure. Regarding the former, as blockchain-specific records include the block height as a version prefix, they are naturally ordered and multi-versioned. Therefore, ChainDash uses an append-only storage layout to sequentially store the temporal data, without the need for background compaction to merge redundant records and reorder. Each file of the store holds temporal data within a specific block height range, and multiple consecutive files logically belong to the same epoch. The window-based graph queries need to quickly determine the existence of neighbor vertices within the queried version range. However, maintaining the filtering structure per file is inefficient, because traversing each filter results in costly overhead. Therefore, the store built an index for each epoch, which combines Contmin Sketch and Bloom filter to support fast and space-efficient filtering with a low false positive rate. To evaluate the performance of window-based graph queries, we compare ChainDash with Nebula. The results show that ChainDash outperforms Nebula with an average latency saving of 34% for one-hop queries, and shows a more evident advantage with average latency savings of 47% and 41% respectively for 3-hop and 5-hop queries. In summary, we propose ChainDash, a blockchain-specific data analytics system. It supports efficient ad hoc graph analytics for applications like KYT. By parallelizing the data synchronization and optimizing the graph snapshot retrieval, ChainDash can effectively meet the demand for ad hoc graph analytics of arbitrary time windows. Now, we show the visualization interfaces of ChainDash, where attendees can view statistical information from the dashboard and execute customized graph queries by filling out the form. For example, when we click the search button, ChainDash will execute a 2-hop query and generate an overview of internal smart contract activities. The queried result is represented as a network consisting of multiple vertices and edges. In addition, the pie chart displays the distribution of vertices with different degrees in the network. In the overview mentioned, we know that some addresses have a high volume of transactional activities in a short time, and more detailed analytics for them are required. In this case, filtering rules enable customized anomaly detection from various perspectives, such as time range and transfer amount. So when we fill out the form below and click the search button, an abnormal behavior network graph is generated in the Analyze view. As different address types are marked with different icons and transaction information is labeled, attendees can easily observe the flow of funds. In some illegal activities such as money laundering and fraud, this helps to effectively intervene before funds are involved in coin mixing or cross-chain transactions, thereby avoiding greater economic losses. That's all. Thanks for your attention.